welcome to my talk. So this is about scalable bias-resistant distributed randomness. And this is joint work with many people from Trinity College, from EPFL, from University of Bonn in Germany, and from Yale University. So my talk has like four big sections. First of all, I will give you a motivation and tell you why do we need public randomness and why is the generation of public randomness hard. Then I will present two randomness protocols that we designed. Then in the third part, I will talk about the implementation and our experimental results. And I will conclude my talk with a short demo and with a summary. All right, so let's start. Why is it hard? Why do we need public randomness and why is the generation hard? So in general, we distinguish between two types of randomness. On the one hand, there is secret randomness that you generate for yourself, and then you keep that randomness secret because you want to derive like encryption keys from that, right? And you don't want that your adversary ever knows what the random seed was, so that he cannot like derive the private key. On the other hand, public randomness is only kept secret up to a certain point in time. And up to that point in time, it has to be unpredictable. Afterwards, you reveal that randomness and you use it collectively. So for that kind of randomness, just having good entropy is not enough. For public randomness, you have like a lot of applications. And here are four big categories. First of all, you can do random selection. So you can run lotteries, or you can use it for voting and election audits. Then you can also use it for games, for example, to shuffle your decks. You can use it for protocols, for example, to choose parameters, initialization vectors or nonces, or you can also use it for sharding. And you can also, in the final category, you can also use it for crypto. For example, for challenges and zero-knowledge proofs, for authentication protocols, and so on. If you want to learn more about applications of this public randomness, I encourage you to stay also for the next talk, because my colleague Lefteris will present some concrete applications of public randomness to blockchains. So people use this public randomness already for quite some time, and of course people also misuse these systems. So here are some examples on failed or rigged randomness applications. So during the Vietnam War draft lottery, the numbers representing birth dates were not sufficiently mixed before drawing the order to appear for induction, which as a consequence led to the outcome that people who were born in December were more likely to be picked to go to war than those who were born in January. For one of the European soccer competitions, they had a big urn where they put in the balls, from which one of the organizers of the lottery would pick the balls. And it turns out that they were heating and cooling down those balls in there. So when the person would go into the urn, the person could directly feel if it was a hot or a cold ball. And then even if you have like public witnesses, there is no way you can see that the lottery was actually rigged. And a final example, there are also insider attacks where, for example, in one case, there was a software developer who hacked the random number generator, which was used to choose the winning numbers in the Megabucks lottery. So I don't know if Ronan is here, but to run a raffle, for next year, let's reconsider the approach, okay? So public randomness is not new, right? So for example, in 1955, there was a large book with a table of randomness sold by a corporation called the Rand Corporation. And then you could just use these random numbers that were published in that book. So of course today we still need public randomness, but just getting public randomness that you bought from a book is of course not enough. So public randomness, generating public randomness is really hard, and the main issues that you face are the issues of trust and scale, both in the generation and the usage. So when we set out to design our protocols, we wanted to work in the familiar and very well understood T of N threshold security model, and we had 5 specific goals in mind. First of all, availability, so that we guarantee a successful protocol termination as long as there are at most T minus N dishonest nodes. We also want to achieve unpredictability so that the output of the protocol is not revealed prematurely. We also want to achieve unbiasability so that the output is distributed uniformly at random despite any potential interference from an active adversary. We also want to achieve public verifiability so that anyone can check the correctness of the produced randomness. And finally, we also want to achieve scalability so that the randomness can be generated among a potentially very large number of participants to increase the trustworthiness of the generated randomness, because we don't want to just trust a small set of nodes. So there are already quite a few approaches on how to generate public randomness. One category is where you rely on a trusted third party, and the NIST randomness beacon is one example for that, right? You have to trust NIST that they are generating the randomness in a benign way and that they are not cheating. But that is not what we are trying to do here. We want to go without a trusted third party. So, and there are also a few approaches how to do that, including you can rely on Bitcoin to generate this public randomness, or you can use slow cryptographic hash functions. You can also use like regular lotteries or even financial data. But these are all kind of unusual trust assumptions. So in the same security model that we are concerned with, the T of N threshold security model, there are also approaches like coin flipping or distributed key generation. But the problem here is that these approaches usually do not scale well past like tens of participants. But we want to achieve here hundreds or thousands of participants who run these protocols. So at first, generating public randomness seems easy, right? You just say, okay, I have these nodes and they all generate a random value, and then we combine all these outputs to get the final random string. The problem, however, is that the last node in this sequence completely controls the output. So the adversary can't just wait until he sees the outputs of n-1 nodes, then some, for example, XOR everything together and then choose his random string in such a way that the outcome is to his liking. So that's not a good approach. So we can fix this issue by going to a commit then reveal scheme. So we first commit to our random strings and then we open up our commitments and combine them. However, again, the last participant, if he does not like what he's seeing, he can just choose not to reveal his output and therefore abort the protocol and force it to restart, which is also a way to bias the protocol or the randomness. So it does achieve unpredictability, but it does not achieve any of the 4 other properties that we want. Then a next step for our strawman protocols is that we introduce secret sharing, where we share some random inputs. However, a dishonest node, they can't just send bad shares to their to the other nodes in the protocol, and thereby force them to not recover the correct random values. So that's also not good. It achieves already availability and unpredictability, but not unbiasability, because different nodes in the protocol might recover different values, different random values. So this leads us to RandShare, a protocol that achieves availability, unpredictability, and unbiasability. It is a leaderless asynchronous protocol, And it uses verifiable secret sharing so that the participants in the protocol, they can check if a share is correct. And this is not a new approach. This has been done already in the past, but it still suffers from two main issues. Namely, while the output is verifiable by the participants of the protocol, it's not publicly verifiable. So I cannot take that output and go to somebody else and tell him, look, this output was generated in a benign way. And moreover, it does not scale very well. Namely, it has cubic communication and computation complexity. So coming to the main part of our talk, where I will present two randomness protocols which target different deployment scenarios. The first of all is RandHerd. And with RandHerd, the two main things that we target is verifiability by third parties. I can take the random value, go to somebody else, and convince him that this random string was generated in a benign way. And also scalability. We want to have a lot better performance than this O of n cubed. So in how RandHerd works, it's a client-server randomness scavenging protocol where an untrusted client uses a large set of nearly stateless servers to generate this verifiable randomness. And therefore, the client generates a configuration file which specifies like which servers are participating in this randomness generation run and also the purpose of the randomness. And then he's sending this configuration files to the nodes, and thereby he's starting the protocol. And this is a one-shot approach. So if the client fails to finish that protocol, then all kinds of alarm bells should go off, and he also is forced to regenerate this configuration file. He cannot reuse the same configuration file. So for example, consider a lottery authority which wants to pick a winner in a fair and verifiable process. Then the setup is a client or the lottery authority, it would announce in advance, let's say, in 1 week from now, we are doing this lottery mechanism, and I'm setting up this configuration file, and I put it somewhere on a public bulletin board saying, okay, everybody can verify this configuration file. And in 1 week from now, we do this randomness generation. And then the client runs together with the servers this protocol and generates the verifiable choice. So how do we achieve these two properties, verifiability and scalability? First, verifiability. We make use of two building blocks. Namely, first of all, we use public verifiable secret sharing, which is a variant of Shamir secret sharing, but it comes with zero-knowledge proofs. So that the shares, they are encrypted and publicly verifiable through these zero-knowledge proofs. And this allows the client to orchestrate this protocol, and there is no communication necessary between the servers. And in the course of the protocol run, since all the messages go through the client and everything is publicly verifiable, the client creates a third-party verifiable transcript of the protocol run that he can later on then present to third parties to make the randomness verifiable. Additionally, we also use collective signing, which is basically aggregate Schnorr signatures to force the client to publicly commit to his choices during the protocol run to avoid a client equivocation attack. Yes, so the client, as I already mentioned, he is creating this protocol transcript that's publicly verifiable. So to achieve scalability, in RandHerd, the output is a function of all the input values from all the servers. And the secret sharing allows to deal with a certain number of unavailable servers in that scenario. However, the secret sharing, if I have like hundreds or thousands of servers, then the secret sharing among all servers is very inefficient. And it will result in an unacceptable computation and communication complexity. And therefore, we group the servers together in PVSS groups, and only do the sharing within the PBSS groups. And then the output of the protocol is we basically combine the outputs of every group to create the final output of the randomness protocol. However, this leads to a chicken and egg problem. So, namely, how do we securely assign the participants to groups? Because ideally, we do not want that the adversary can control one of these groups fully, right? Because then bad things might happen. So for that, ideally, we want to distribute the servers randomly to those groups in an unbiasable way. But this leads to this chicken and egg problem because we wanted to run the RandHerd protocol to generate this random string in the first place. So what do? To solve this problem, we just let the client select the server grouping, and we designed RandHerd in such a way that at most the availability might be affected. So all the client can do is self-DOS himself. So he can say, okay, I run this protocol, and then when he's screwing up the grouping, then yeah, the protocol fails, but that's not in the incentive of the client. So, and we achieve the security through two properties, namely once through the pigeonhole principle, by saying that since we have an honest majority and we assume an honest majority in the servers, at least one group is not controlled by the adversary, and therefore we get a good random value out of that group, which randomizes the final outcome. And we also, as I already mentioned, we use collective signing to prevent client equivocation so that he cannot generate with one protocol run, let's say, 2 transcripts or two random values plus a transcript, which are both legit. So as a summary, RandHerd already offers all the properties we set out to achieve. And specifically, it offers a linear complexity, assuming a constant group size so the subgroup size has to be constant. And it's already a significant improvement over prior approaches. So in the next part, we'll further consider how to achieve even better scalability. So in the previous protocol, randomness is produced on demand, right? We have these randomness servers sitting there, and at some point a client comes along and says, okay, now we generate a new random value. So it's on demand. And the process is driven by a client who is fully in charge and responsible for the protocol run. So in our second protocol, RandHerd, we want to be able to generate a continuous randomness stream without the need to make one of the nodes fully responsible for the protocol run. And although RandHerd relies on a leader, it's only trusted with availability to simply coordinate the process among the participants. So, and ideally what we also want to get is, in RandHerd, we have this protocol transcript, which is basically we are collecting all the messages that we see in the protocol. So but here we also want to reduce the proof size that we need for our randomness. And ideally we want to just have a single Schnorr signature as the proof that the randomness is correct. And we also want to have better performance than this O of n. So, and how we do that is we designed RandHerd to be a decentralized randomness beacon, and it's built as a collective authority, or a coauthority short. And RandHerd can generate randomness on demand at frequent intervals or both. And the idea is that the collective randomness is basically nothing but a collective Schnorr signature from where all the participants contribute to the output. The benefits is that the proof is very small, and it gives you logarithmic complexity because we're running this over a communication tree. However, the problem is that if one of those nodes fails, then it can influence the outcome because the node's contribution to the final randomness is missing. That's what we don't want to achieve, right? So the solution for this problem is that we arrange, again, all the participants in the protocol in secret sharing groups, in threshold signing groups. And then the collective randomness is basically the aggregate group signatures of all the outputs of all the groups. And how we do that is we first have a setup function, and then we have a round function which generates the randomness. Coming to the setup, first of all, we have our nodes, and we pick one of those nodes as a temporary leader by running a VRF-based lottery. So VRF is a verifiable random function, and then at a certain point in time, all the nodes, they generate a VRF. And so you can think of a VRF as a public hash function. So the output is unpredictable to other participants, but everybody can verify the output. So now everybody generates these tickets, and we arrange them in increasing order, and then we just say, okay, the lowest winning ticket, the ticket with the lowest value is the leader for the next step. So in step 2, we use RandHound, where the just elected leader is the client, to generate a public random string among all the servers. From that, we shard all the participants into subgroups, and each of these subgroups is running basically a distributed key generation protocol to set up this threshold signing group. And finally, the output of this process are that every group has a group key here denoted by the x0, x1, and x2. And in the final step, we use a collective signing, or shortly COSI, to certify the aggregate public key, which is basically just the sum or the multiplication of all the group keys, which gives you this final key. And we put that's basically a collective Schnorr signature. So and once that's done, we can switch to randomness generation, where one of these nodes temporarily works as a authority leader, and it broadcasts a series of timestamps, which then will get signed by all the subgroups. So this V will be signed by the yellow group, by the blue group, and by the green group, and they all produce their collective Schnorr, their threshold Schnorr signatures, and then we sum up these Schnorr signatures to get an aggregate signature, and then we publish this aggregate signature as the collective randomness, which can be verified against the public key that we generated during the setup. So as a summary, RandHerd achieves all these properties that we set out to achieve, and specifically it achieves logarithmic complexity if the group size C is constant. So we also, in the next part, I present the implementation and experimental results of our 2 protocols. So we implemented all the 2 protocols and and all the necessary building blocks in Go. And we integrated this in the DDIS, so the Decentralized and Distributed Systems Lab code, which consists of a crypto library, a network library, and the authority framework, which specifies the protocols. And if you're interested in that, you can check out this GitHub link where everything is publicly available. And to run the experiments, we ran that on DTLab using 32 physical machines. And to simulate a more real world deployment, we restricted the networks to 100 megabits per second bandwidth and to a 200 millisecond round trip latency. So this first graph shows you the RandHound randomness generation and verification. So here on the x-axis, you see here on the lower part, you see group sizes, and here on the upper part, you see the number of nodes. So we did experiments for 128 to 1024 nodes. And here on the y-axis, you see the wall clock time, so basically the latency in seconds that it takes to generate random and verify randomness. So as a takeaway, for one RandHound run and 1024 nodes and a group size of 32, it takes 290 seconds to generate this randomness and 160 seconds to verify it. That sounds like a little bit much, but remember that RandHound is really just a once-in-a-while protocol. So you use it to generate this publicly verifiable seed, and then you do something else with that. So we don't assume that we run this every few seconds, but let's say you run it once a day or something like that. So this graph, again, has the same x-axis, and the y-axis shows the CPU usage in seconds. And here, again, the takeaway is that one RandHound run amounts to roughly 10 CPU minutes to execute, which is less than 2 cents on Amazon EC2 for 1024 nodes and a group size of 32. Then we also evaluated the RandHerd protocol. Here you can see the randomness generation for RandHerd. And here, as a takeaway, it takes for one RandHerd run, it takes 6 seconds to generate the randomness after a one-time setup using RandHerd, which takes roughly 10 minutes for 1024 nodes and a group size of 32. So here you can see this trade-off that we are doing. We have first an expensive setup, but afterwards we can very efficiently generate randomness at very frequent intervals. Okay, and here you can see this graph shows the logarithmic complexity for randomness generation in RandHerd, also given a constant group size. So coming to the end of my talk, first of all, let me show you a quick demo. So we set up a proof of concept a randomness beacon. So here in the middle, you see the latest random value that is generated. It's a 32. Maybe I can increase it a little bit. Let's see if this works. Yeah. So here you can see the latest randomness value that was generated. And here you also see like this bar is basically, it shows you that every 30 seconds a new random value is generated. So we artificially slowed it down to 30 seconds. It could generate randomness much faster, but 30 seconds for the demo is enough. And then we also collect like the randomness that's generated during one entire day. And you can basically browse it here. You can go through all the random values that were generated during one day, and at the end of the day, we reset it and start anew. So the thing is that, of course, here in the browser, you cannot verify the randomness, right? Because you have this bootstrapping process problem. How do you get the JavaScript that's needed for verifying the randomness to the endpoint to verify? That's, again, a chicken and egg problem. So what you want to do is you download our client code, compile it on your machine, and then the client code allows you to get the latest random value from our authority and verify it locally if you want to use that. And yeah, what can I say? We already have a happy customer. So this is Diego. He's a cryptographer in Latin America. And he said, yeah, yesterday I used Pulsar to shuffle the seminar presentation order in my introductory crypto course. So yeah, people are already using that. That's great. So as a conclusion, I hope I could convince you that generation of public randomness is really hard and it faces trust and scale issues. And I presented two protocols to you in the very well-known T of N threshold security model, namely RandHound, which is an on-demand protocol and achieves a linear complexity, and then RandHerd, which functions as an efficient randomness beacon with logarithmic complexity. So, and for further for the demo and the code, you can check out pulsar.dedis.ch. And yeah, that's it from my side. Thanks a lot. And
Thank you,
I'm happy
Philipp.
to take your question.
Anybody has any questions?
So you mentioned the chicken and egg problem when I used the website. You said the solution is to have a compiled client on my machine and that contacts your server for the random value. How can I be sure there's no middleman who pretends that I'm contacting your server and sends its own random value? Yeah, okay, so yeah, for that you of course need to somehow verify the authenticity of the nodes, and we assume that like in this configuration file that I mentioned, that includes all the public keys of the authority. So this is not like, that's not an open, completely open system. We assume that the nodes participating in the randomness beacon, they are well known, and that you get this configuration file through a secure channel.
Thank you.
Okay, thanks.